Good day everyone. In this video, we will be discussing on installing and configuring Windows Debugger. We will then initiate an user dump on our installed SQL Server and then view its content on the Windows Debugger. Let's get started. Let's first install the Windows Debugger. Let's get into this particular link. Put in this link to the article in the description. So we basically have to download the ISO file as part of your Windows SDK. Once downloaded, you will see this ISO file. Just double click on that, and then you just need to open this Win SDK setup. So right now I'm going to install it on the C drive program files. So if we look at it here right now, the estimated disk space required for installing this is like 3.6 GB. But since we are just worried about Windows Debugger here, I'm going to select only that, and everything else I will be excluding. So let me click on next. And then just leave the defaults and then accept the license agreement. And here, what I'm going to do is like I'm just going to keep debugging tools for Windows, and I'm going to uncheck everything else. So let me uncheck the things that are not required for me. So right now what I'm seeing is like it has come down, the estimated disk space has come down from 3.6 GB to 567 MB. So let me start the installation. Once the installation is completed, what we'll do is like we will open the Windows debugger, load the required public symbols, and also like initiate an user dump on the SQL server, and then we will view it. So right now the installation is completed fine. So let me try opening the Windows debugger. So what I'm seeing is like um, if I just type WinDBG, I'm able to see like I have a 64-bit installed WinDBG. So I'm going to open that. And once I have the dump file, what I'll do is like I will open that dump file in this debugger, and then we will have a look. So before that, what we'll do is like let's create an dump file. So in this one, it's a lab machine. I'm going to create a dump file here. So let me execute the command dbcc stack dump. This is completed. So what I'll do, I will check the location where the dump file is present, and then we will take it forward. So right now what I'm seeing is like there is an dump created. It is basically mentioning like it's an user initiated stack dump and not a server exception. So let me go to the log folder. Let me get the details of the log folder, and then let me try opening that. So if I go there and then look for the date modified, what I'm able to see is like there is something called SQL dumps 002.mdmp. It's like created at 9:53 p.m. So this is the dump that we have created. Okay. So what I'll do is like I'll copy the location and then go to the WinDBG and then go to file and then click on open crash dump, and then open this particular MDMP file that is created. So this is loaded now. So what I'll do first is like I would basically like load the public symbols. The symbols is kind of a language that basically resolves all your stack and things like that. So what I'll do is like let me execute this command to load the symbols. Again, I'll put in this information like what command I basically have to run for loading the symbol in the description. And what I'm doing is like this command is going to download the public symbols to a folder called C drive JVS wiki underscore public underscore symbols. If you want a different drive and a different folder name, you guys can definitely change that. So let me run that. It's going to take some time to download. So in my case, it is completed now. So what I'll do next is like I would reload the symbols. So the command for that is dot reload /f. This is going to take good amount of time depending upon your an internet speed, and also like it is going to download all the required symbol files, at least for this particular dump. So it's gonna take time. Okay, I had to pause the video because it took close to 15 minutes for the symbols to load. So it's done now. So let's look at the location. Let's go to the C drive and then check the JVS Wiki public symbols. This is the one that I've utilized. So if we can see here, all the public symbols required are all downloaded here. So there is huge symbols that were downloaded. So that's the reason it took good amount of time. So let's try if the symbols are loaded properly. So let's try a command lmvm SQL Server. And then what I'm able to see is like the product version is like 15.04236, which is basically SQL Server 2019. Let's check that once. And what I'm able to see is like it's same here, 15.0424236. So I'm pretty sure like the symbols are loaded fine. So what we'll do is like let's do some basic checks on this particular dump file. So what I'll do is like I will use the tilde symbol. So that basically lists you all the threads that is present on this particular dump file. To be clear, this is an user-initiated dump file, and it's not an exception. Like it's not a dump file created due to an exception, like maybe an access violation, non-yielding scheduler, deadlock scheduler, etc. It is just a dump that was taken. We usually use user-initiated dumps. For example, if we feel like there is something wrong happening on the SQL Server, so what we basically do is like we take 3 or 4 user-initiated dumps with a frequency of like maybe 4 to 5 minutes each, and then we will be looking at these dumps to understand what is going on. But for this video, I've just taken one dump, and I just want to show like how do we install Windows Debugger, and then how do we configure it. So right now we use the tilde symbol and then listed all the threads available on this particular dump file. So next what we'll do is like we will get into one of the threads here. So in this case, I'm going to do a tilde 79s, and then I'll be getting into this particular thread. If you notice here, previously it was 27, and now after I typed tilde 79s, I'm able to see like have entered into the thread 79. So if we put in a command called kc, then you will be able to look at the stack for this particular thread. So that's it for this video. We will talk about process, threads, scheduling, quantum, context switches on our next video. We'll be discussing on process, threads, scheduling, quantum, and context switches on this particular video. Let's get started. Consider I'm using a server that has got only one CPU core on it. Listening to music using VLC media player, using OneNote, browsing internet, running SQL Server in the background. It will all be kind of seamless, wherein I'll be able to hear music, check OneNote. SQL Server can be accessed using SQL Server Management Studio, and then I can browse the internet all at the same time. But in reality, what happens is like a processor can execute only one thread at a time. It basically completes, or it basically runs a thread, executes a thread on the processor, and then moves on to another thread. And the execution happens strictly one at a time. There is no way a processor can execute multiple threads at the same time. If we talk about process, a process is an encapsulation of one or more threads. Process in real world can be compared to a team which comprises of one or more team members who all have a common goal to achieve. So each member in the team will get a task they basically have to complete individually, which in turn will result in the final goal completion. A process is same as a team, wherein it has got several team members within it. So for example, a process uh, is compared as a team, and the team members are all compared as a thread. A process will have a process ID, memory space allocated to it, and doesn't do any actual work. It is basically a container where threads will be present, and these threads basically performs all the work, like the threads within the process that performs the actual work. Let's take an example. Let's take Outlook as an example here, where while you are using Outlook, a thread will basically be responsible for sending and receiving emails. A thread will be there for an email that we are composing. One thread will be responsible for the spell checks, and another thread may be responsible for the rule check that is configured. And there can be many other threads for several other functionalities within Outlook. So in a nutshell, all these threads will be running in the background and make sure like all the functionalities within the Outlook is working fine. So Outlook is a process here, and then the individual functionality within Outlook gets executed by these thread. So let's look at one particular application. In our case, let's look at Edge. What I'll do is like I will download Process Explorer, and then what we can do is like we can look Edge within this Process Explorer. So if we open this Process Explorer tool, it basically shows you all the process that is running on this particular server. So let's get to Edge here. So maybe like let me minimize this one. And then we have Edge here. So what I'll do is like I will right click on msh.exe and then click on properties. We have several tabs associated with this process, like image, performance, many other things. The one that I'm interested is threads, which we are discussing right now. So what we can see here is like there are so many threads associated with this application. So TID refers to the thread ID. So if we just look at one particular thread, we will be able to look at the stack for that particular thread. So as I told you earlier, process is just a container. It is the threads that is present within this process actually performs the work. So as far as MS Edge is concerned, this particular application holds this many threads that we are seeing here, and these individual threads actually performs the work. Yep, moving on. Let me close the Process Explorer. So how does CPU manage all these threads and schedule it for running? So each CPU will have a list of threads, and that needs to be executed in a list called ready list. CPU executes these threads using a first in, first out approach. That is, the thread that comes first is executed, and once the execution is completed, it will be added back to the top of the list once the quantum of that particular thread is complete. So as an example, if we look at it again here, so right now we have a thread from VLC, a thread from Outlook, a thread from OneNote, and then a thread from Edge. So if we look at this particular diagram here, what we can see is like the thread with respect to Edge came first, next OneNote, next Outlook, and then next VLC. So what happens is like the thread associated with Edge gets executed on the CPU, and then once its quantum is over, what will happen is like this will be added at the top of the ready list, and then OneNote thread will be given a chance. And once that is executed for its given quantum, what it will basically do is like once the quantum is reached, it will go to the top of the list and get it added on top of the Edge thread. And the same process happens for the other thread also. Yeah, this is how we will be having threads executing on a CPU. But just to understand, we are discussing about a server which has got only one CPU core. Okay, let's consider we have multiple CPUs on a server. So let's consider we have two CPUs, okay? Each CPU will have its own ready list and follows the same thread scheduling method as discussed previously. So in this diagram here, what we are able to see is like the first CPU is basically having a thread from VLC, Outlook, OneNote, and then from Edge. The second CPU is having a thread from Outlook, VLC, OneNote, Edge. So what happens is like each of these CPUs execute each of these threads, and once the thread reaches its quantum, it basically adds to the top of the ready list for that particular CPU. So that is how the scheduling happens as far as the CPU is concerned. Yep. So each of these application will basically tell Windows that it has this many number of threads, and then Windows will basically schedule these threads on all the available CPUs where possible. So now let's discuss quantum. Now, what is a quantum that we are discussing right now? Quantum is the time duration that a thread gets to execute on the CPU, after which it has to move away from the CPU and allow the CPU to be used by other threads and get it added to the last position of the CPU's ready list if it has more work to do. If all its work is done, so let's consider the thread which is executing on the CPU. If it has more work to do after it reaches its quantum, what it basically does is like it adds it to the top of the CPU ready list and then allows the next thread to execute. For example, once a thread reaches its quantum, let's consider there is no other work, like all the work associated with that thread is completed, then what happens is like it completes its quantum and then it moves away from the scheduling at all. Yep. Then it basically finishes and kind of moves away from the list altogether. So normally it is 4 milliseconds for every third and is dependent on operating system, CPU speed, and it normally varies between different CPU generation also. So if we look here, the thread executes for 4 milliseconds and then comes out of the CPU, even though it needs more time to complete. This is called preemptive scheduling. Let's consider I have a thread which will complete all its work in maybe like 8 milliseconds. In this case, this thread will execute for 4 milliseconds, and after its quantum of 4 milliseconds is done, it will save its execution context on the CPU and moves out of the CPU and adds it to the top of the CPU's ready list and wait for its turn to again execute on the CPU. Now, once its turn comes, the thread restores its previous execution context from the CPU and then executes again on the CPU. This time, since it is considered like it will require only uh, 8 milliseconds, it has completed its first quantum, and then when it executes one more time, its second quantum of 4 milliseconds completes, and that means like it has completed 8 milliseconds, and that way it has completed all its work and it announces its completion and completely moves out of the CPU. For example, let's consider we have through let's consider we have two threads, T1 and T2 on the ready list, okay? And T1 executes on the CPU, and after 4 milliseconds, it basically yields and then adds it to the top of the CPU ready list. While T1 moves out of the CPU, it will save its execution context. Now, when T2, the thread 2 gets its chance, it will basically restores its execution context saved earlier and starts the execution on the CPU from where it actually left the last time. So this process of saving one's execution context and restoring another execution context is basically called context switching. Yep. In this video, we will talk about scheduling in terms of SQL Server. Let's get started. If we remember what we discussed on our last video and how thread gets scheduled on a CPU, how long it stays and when it yields, the main question that might come to our mind is what will happen to the executing thread if some resource it needs is not available? That thread will be on the CPU and will just wait on the CPU without executing or performing anything, and then yields after 4 milliseconds or whatever is the quantum, as it is not able to run, as the resource it is looking for is taken by something else or maybe a different process or a different thread. To put things in perspective, let's consider we have one update statement on an object called table1 that is using one thread, and then close to 10 select on table 1, object table 1 using 10 threads executing with a default isolation model of read committer. Yep. So we know each select uses one threads. If the SQL Server utilizes the preemptive scheduling of scheduling all its threads, then that means like it will be presenting all the 11 threads, that is one for update and then 10 for the select, will all be there on the CPU ready list in case if SQL Server is going to utilize completely, that is, it is completely based on the preemptive scheduling of the windows. Now let's consider that the update thread that we are seeing here at the end of the ready queue is running on the CPU. Let's consider it as running on the CPU for 4 milliseconds, okay? And what will happen is like it will basically run for 4 milliseconds or whatever the quantum is. And once it quantum is complete, what it will do is like basically this update statement will be added to the top of the ready queue. And then what happens is like the next select statement or the next thread that is going to execute the select statement will be moving to the CPU processor. So in this case, what will happen is like now that this update statement on object one is holding an update lock, what will happen is like this select statement will basically has to wait because it will not be able to take a shared lock as a conflicting lock is already taken by the update statement. In this case, what will happen is like if this is scheduled this way, like when SQL Server presents all its thread, which is not the case as far as the real SQL Server scheduling is concerned, but just in case if we think like that, what will happen is like this select statement will be there on the CPU for 4 milliseconds. And then once its quantum is done, then it will go on to the top of the ready queue and the next select statement comes in. And likewise, all other select statement will be just waiting on the CPU without doing any work, and then it will be added back to the ready queue. So as we know, like since it is all waiting due to this conflicting lock, there is no way we will be able to solve it if we present all the threads from SQL Server to CPU, because what will happen is like for this particular single update statement to complete, all the select statements will have to wait till then. So in that case, there is a problem if we send all the 21 threads directly to the CPU. So in this particular case, 10 threads executing the select statement will basically waste 10 into 4 milliseconds quantum, which is close to 40 milliseconds. And this wastage will go on till the update statement finishes its work. This will be the case if SQL Server uses preemptive scheduling process. Yeah. But just think of a way what will happen if we don't introduce all the 11 threads of, let's say, like at least the 10 threads of the select statement to the Windows and just let the update statement thread to run on the CPU. In that case, we will not see any kind of CPU wastage by the select statement, and this update statement can complete faster. This is the reason SQL Server will not introduce all its available threads, but only one thread of SQL Server per CPU that is available at the top of the SQL Server ready list. This kind of scheduling by SQL Server is called non-preemptive scheduling. SQL Server developers realize that introducing all its threads at a time to Windows will result in costly context switches frequently and end up wasting the CPU resources as advised previously. So they decided to utilize non-preemptive scheduling instead of solely dependent on Windows preemptive scheduling. So SQL Server will handle all its thread efficiently possible internally, and then SQL Server design introduces only limited threads at any point in time to Windows scheduler. How did they do this? They basically utilized a C++ code that calls function wait or wait for infinite, which Windows will not schedule and basically ignore those threads from scheduling. Let's load a dump. Let's use the same dump that we have created before, like we tried creating a user initiated dump. So let's use the same thing. And what we will see is like, let's look at the stack and see what are the threads basically waiting on. Yeah. So I've already loaded the dump. In case if you have any questions how to configure Windows debugger, then you will have to watch my first video. Okay, so let me look at how many threads we have on as far as this user initiated dump is concerned. I'm able to see close to 106. So if we look at any threads here randomly, what will happen is like we will be able to see that these threads are basically waiting on the wait function, which tells the Windows not to schedule on the scheduler. Yeah, so let's try looking at any random thread. Let's say 78 this time. And if I do a KC, what I can see is like it is basically using the wait function, anti-signal and wait for single object. Okay, let's try one more. This time, what we can select, okay, let's do 60. And then let me try a KC here and same. This is also waiting on anti-wait for single object, yeah. And this would be the last one. Let's try the last thread, which is 106. And what is this doing? It is again doing the same thing, anti-wait for single object. So this way, what we are basically doing is like we are calling, let's consider like what are threads that is not considered to be scheduled as far as SQL Server is concerned. So these threads basically calls the wait function, which in turn makes the Windows not scheduling these threads. So that is how this is achieved by the SQL developers. So as discussed before, we cannot hide threads of any application from Windows. What SQL Server does is it will make sure that the threads that are not ready for the from SQL Server perspective will all wait using wait function, which in turn will make Windows not to schedule these threads. If we get more deeper into this, SQL Server will maintain a gateway, which in turn has got 5 queues, and these 5 queues are runnable queue, waiter queue, IO queue, timer queue, and then the last one is worker queue. So if we talk about runnable queue, this queue contains threads that are ready to execute, but its turn on the CPU is not yet arrived. So these threads are ready and are not waiting on anything, has all the resources required for the execution, but it is just waiting for its turn on the CPU. Next one comes as the waiter queue. So this queue contains threads that are blocked, that is, they are waiting on a resource due to a conflicting lock. Any thread that are waiting on something will be placed in this queue. So for example, when you run a sp underscore who or a dmv sysdm exec request, you will be seeing some threads on suspended status. So those threads basically will be present in the waiter queue. The next one comes in the list is IO queue. And this queue contains threads that are waiting, that are basically waiting for IO completion. Next one is timer queue. This queue contains threads that are on a scheduler, for example, a thread that will wake up for every 5 or 10 seconds and has to do something. For example, you execute a wait for delay. These threads will all be placed here. Next one, the final one would be the worker queue. So this queue contains requests that are waiting for a free worker thread. SQL Server is designed in a way to present only one thread at any point of time, that is at the bottom of the runnable queue to Windows, that is the CPU. All other threads in the runnable queue will be calling wait for infinite, and that way Windows will not be scheduling those threads. Now, when this one thread goes to CPU, it will compete among other threads from other application and execute for say one quantum or maybe two quantum or maybe n quantum before it reaches its yield point. This yield point for a thread will be defined on the SQL Server code, and depending on that, after certain quantum, this particular thread belonging to SQL Server will add it to the top of the SQL Server runnable queue if it has more work to do or is not blocked by anything else. Let's consider that SQL Server thread executing is looking for something that is not available at that time or is blocked by something else. Then it yields and moves to the SQL Server waiter list this time. Same way, if the SQL Server thread executing on the CPU requires an IO to be completed, Then in this case, it yields and adds it to the SQL Server IO list, and the next thread at the bottom of the SQL Server runnable queue will now get to the Windows CPU and compete among other threads from other application as discussed previously. Whenever a SQL Server thread yields, before getting into one of the SQL Server queue, it needs to perform some sort of a janitor task. So janitor task refers to the task that the yielded thread should perform. Basically, it moves the last thread in the runnable queue to the Windows CPU, then check other queues such as waiter, IO, timer, and the worker queue to see if any of the threads that are ready, and if yes, then pushes it to the runnable queue. For example, it checks the IO queue. In case the IO that the thread is waiting for is complete, then it pushes that particular thread to the runnable queue and then adds itself to the required SQL Server. One thing to understand is, even though we present one SQL Server related thread per Windows CPU, if there are many non-SQL Server threads on Windows CPU ready list, then there is high possibility we might not be able to perform well. That is, the SQL thread will not be performing that great, as we will be spending much time at the ready list rather than executing on the CPU. So this could be like compared with the signal weight that we are seeing. So we will be ready to execute on the CPU, but if we are not getting the chance to execute on the CPU because of other threads, then this could be a problem. This is the main reason we follow a best practice that we shouldn't install any unwanted application on a database server. We discussed on our last video about scheduling in terms of SQL Server. We will continue on the same topic on this video too. Let's get started. What is a scheduler in terms of SQL Server? Scheduler means presenting one thread per CPU. This implies that we will have one scheduler for each available CPU on the database server. Even though SQL Server utilizes non-preemptive scheduling, but the underlying scheduler on the Windows server, which is basically your CPU, will be preemptive, as Windows uses preemptive scheduling. Preemptive scheduling works with respect to the priority of the thread. All SQL Server thread will have a normal priority, and it can be bumped to real time by selecting Boost SQL Server priority option. I'm discussing this just for information, but we never do this, as increasing SQL Server thread priority might hinder important Windows thread, and this could lead to availability issues. That is, SQL Server might go down, or you might be seeing some sort of situation where you are getting dump files created. As far as Windows is concerned, higher priority threads can preempt currently executing lower priority thread and can schedule itself on the CPU, and this can lead to some thread starvation. But as far as SQL Server is concerned, all its threads will have same priority. SQL Server will beautifully schedule threads across scheduler uniformly without worrying about some schedulers having more and other schedulers having less threads. We have an algorithm that can perform worker switches on latest version of SQL Server during edge cases where some schedulers can have more threads, and some of those threads from those schedulers, which is having more number of threads, will be transferred to a scheduler that has fewer threads. SPIDs, or session IDs that are in suspended state, implies that those threads are on waiter list till the time they are waiting on something. Let's talk about yield condition generally for a SQL Server thread. A thread can yield if it fetches a database page, the worker execution quantum is checked. If it exceeds the 4 milliseconds quantum, then it is basically yielded. The thread yields at every 64 kilobyte count of sort records. A thread can yield if it is going to make an external call to an extended stored procedure or link server. A thread can yield if the client cannot fetch results as fast as they are returned. A thread can yield if it is forced to wait on a latch. A thread again can yield if it completes the run of each statement in a batch. Let's consider a situation where there are no workers on the SQL Server runnable queue. The worker that basically yields from the Windows CPU is allowed another quantum or performs the required idle scheduler maintenance or the janitor task as mentioned before till we see new thread on the SQL Server runnable queue. Moving on, let's talk about scheduler, task, worker, thread, request, sessions, and connection. So scheduler, also known as SOS scheduler, this object that manages thread scheduling in SQL Server and allows thread to be exposed to the CPU. You can get the details of the scheduler by querying dmv sys.dm underscore os underscore schedulers. This is the all-powerful master whom everyone abides to. Scheduler does not control things but lets the workers work with each other and relies on their cooperation. It is also called cooperative scheduling mode. Each scheduler, which is one per logical CPU, accepts new tasks and hands them off to the workers. SOS scheduler also allows one worker at a time to be exposed to the CPU. Tasks. A task represents the work that needs to be performed, and you can look at these tasks by querying the DMV sys.dm underscore os underscore tasks. A task contains one of the following events: a query, RPC event or a language event, a pre-login, kind of a pre-login event, a login, a connect event, a logout, it's a disconnect event, a query cancellation can be an attention event, a bulk load, which is a bulk load event, a distributed transaction, which is a transaction manager event. A task is what the master is about. It is what defines its existence. Note that these are tracked at the SOS scheduler layer. Let's talk about the worker, that is the worker thread. This is logical SQL Server representation of a thread. Maybe think of it as a wrapper on top of the OS thread. It is a structure within the scheduler which maintains SQL Server specific information about what a worker thread does. Querying DMV sys.dm underscore os workers gives a list of worker. Workers are the humble servant who can carry out the task assigned to them by the scheduler. Let's talk about the thread. This is the OS thread that could be found querying by the DMV sys.dm underscore os underscore threads that is created via calls like create thread or begin thread ex. A worker is mapped one-to-one to a thread. Let's talk about request. Request is the logical representation of a query request made from the client application to SQL Server. You can check the request by querying dmv sys.dmexec underscore request. This query request has been assigned to a task that the scheduler hands off to a worker to process. This represents query requests as well as system thread operations like checkpoint, log writer, etc. You will not find login, logouts, attentions here. Also, note that this is a representation at the SQL execution level and not at the SOS scheduler layer. Let's talk about sessions now. When the client application connects to SQL Server, the two sides establishes a connection or a session exactly on which to exchange information. Strictly speaking, a session is not same as an underlying physical connection. It is a SQL Server logical representation of a connection. But for practical purposes, you can think of this as being a connection. You can query sys.dm underscore exec session to get a list of sessions. This is the old SPID, session process ID, that existed in the SQL Server 2000 and earlier. In the case of system sessions, that is the internal session spawned by SQL Server like lazy writer, checkpoint, log writer, service broker, etc. No external physical connection is mapped to the session. Only a session ID exists, typically reserved for session IDs less than 50, but can be a higher value too. You may sometimes notice a single session repeating multiple times in a DME output. This happens because of parallel queries. A parallel query uses the same session to communicate with the client, but on the SQL Server side, multiple worker threads are assigned to the service this query request. So if you see multiple rows with the same session ID, know that the query request is being serviced by multiple threads. A session ID or a SPID is used to identify the work performed inside SQL Server. For example, you may want to find out which session ID is executing a query or which session ID added its query cancel. Some of the property of a session include login time, last request time, CPU consumed, memory consumed, and total elapsed time used by a query or set of queries on this session. Username, set options configured for this session. Let's talk about connection now. Connection is the actual physical connection established at the lower protocol level with all of its characteristics. Querying sys.dm underscore exec underscore connections gives details of the connections. There is a one-to-one mapping between a session and a connection. A connection has some of the following properties like protocol, shared memory, TCP, or named pipes, authentication type, either NTLM or Kerberos, encryption, either switched on or off, network packet size, client IP address, and port. These are all physical properties of the connection. A connection underscore ID in sys.dm underscore exec connection is a GUID and is used to uniquely identify the physical connection. You typically won't use a connection underscore ID to identify which session is executing a query. A session ID is comfortably used instead. Let's now discuss how all of the discussed components previously work together. So a client application creates a physical connection to the SQL server. Then the application sends a pre-login request and the task is created and assigned to a worker to fulfill the required task. Once the server and client finishes the pre-login process, a login request is sent and another task is formed and handed off to a worker thread. Once the login is completed, SQL Server creates a session that represents this logical connection where it will exchange information with the client. When the client application sends a query request, the server again creates a task and assigns it to a worker thread for completion. If the query is cancelled in the middle of the execution for some reasons, the server will receive an attention request upon which the IOCP listener will mark a bit that the query is cancelled and the worker that was running the query would stop executing when it sees this particular big set. If the query is allowed to complete, on the other hand, the client application is done. It can send a disconnect or logout request, which again is packed as a task and serviced by a worker. We will discuss on non-yielding schedulers on this video. Let's get started. As discussed earlier, we present one thread from SQL Server runnable queue to the Windows CPU, and we know that depending on the yield point that is present on our SQL Server code, this thread that is executing on the CPU will have to yield after or before this quantum based on the yield condition. What if a thread executing on the scheduler, let's consider thread 1 is executing on the scheduler, and what if this thread executing on the scheduler doesn't yield even after 60 seconds? In that case, SQL Server understands that there is an issue with this thread and usually generates a non-yielding scheduler message with a dump file which contains more details about the condition. Since we cannot allow any thread to monopolize the CPU, so what happens is like if a thread is executing more than close to 60 seconds on the scheduler, and if it is not gracefully yielding, then what happens is like SQL Server basically generates a condition that there seems to be a problem, and that problem would be the non-yielding scheduler. So what would be the possible reasons for a non-yielding scheduler? bug on the SQL code. So the bug refers here that there is no proper yield point defined on that particular code, and due to which this thread doesn't yield. Reason number two, maybe it is an CLR code, which can cause this problem, wherein it continuously runs and doesn't yield. There is a possibility spin locks can cause this problem. Spin lock implementation is utilized when the thread is looking for a resource, and if it is used by something else, in that case, spin lock will call an empty while loop, and after certain quantums, it will check again till the resource is available. This implementation, as far as spin lock is concerned, is done when access to a resource is expected at a very, very short time. And this avoids context switches, and this basically kind of takes care of the resource contention and things like that. But spin lock will utilize CPU even though it is basically going to wait. That is, it is going to use some quantum before coming back and checking for the resource. And this can lead to a non-yielding condition in some cases where spin lock runs for a longer time. The next point, the next reason could be like it could be like we can get this non-yielding schedulers if there is a thread starvation condition as far as the CPU is concerned. What if there was a high priority thread that is running on the CPU continuously and not letting SQL Server thread to run on the CPU? In this case also, SQL Server thinks that SQL Server thread, which never got a chance to run, is not yielding, or it is basically like there waiting for its CPU. And what happens? SQL Server basically thinks it to be a non-yielding condition. The next reason would be like, what if the Windows VM where the SQL Server is installed is getting into a situation where the whole VM is getting freezed for, say, some minutes or some seconds. Even in this case, SQL Server thinks that the SQL thread is not yielding, depending on the situation. But in reality, the problem seems to be something else. But SQL Server thinks that it could be a problem as far as the SQL thread is concerned, and then non-yielding scheduler situation is kind of called up, and a dump will be generated. SQL Server utilizes schedule monitor that runs every 10 seconds to check for any non-yielding condition on the database server. It creates a non-yielding dump when a particular thread is not yielded even after 60 seconds. If you check the DMV, sys.dm underscore os underscore schedulers, we have a column called yield count. If this value doesn't increment after 60 seconds or say 1 minute, then it is considered that the particular thread has not yielded and the non-yielding scheduler condition is kind of met. SQL Server, as soon as the non-yielding condition is met, it will capture the thread stack as non-yielding call stack, and then captures one more call stack of the thread as current call stack when the dump file is created. Just to repeat the things, it basically captures an initial stack called non-yielding call stack, and then while writing or creating the dump file, it creates another stack within the dump file called current call stack. There will be some seconds difference between these two call stacks capture. So let's consider if both the non-yielding call stack and the current call stack are one and the same, then it proves that it is a definite non-yielding condition as the stack did not change at all. The reason could be anything, maybe in spin lock or VM freeze, but at least we will know like it seems to be a definite non-yielding scheduler condition. But on the other hand, if the non-yielding call stack and the current call stack are somewhat different, then that means that the thread has basically moved. That is, it might have yielded or it has basically moved. And that's the reason we are seeing a different call stack for the current call stack when compared to your non-yielding call stack. In this case, this doesn't seem like a non-yielding condition, but the reason why the thread spent close to 60 seconds on the scheduler should definitely be checked further. We can check the kernel time and user time spent by this thread by analyzing this thread in the sense like the current thread that is executing on the scheduler for say like 60 seconds or so, and that is when we got this non-yielding scheduler condition. Um, we can analyze that particular thread, and we can check for the kernel time and user time spent for that particular thread using the WinDBG on the dub file. If the kernel time is more than the user time, then it implies that the thread has spent more time on the kernel mode, and the problem could be mostly on the operating system. On the other hand, if the user time is more, then that means the code seems to have some issue. The code, that is the underlying code that particular thread is executing, can be an issue. Could be a problem with the SQL Server or that particular process that is running. But if the kernel and user time is kind of both at zero, that is like no time is spent as far as kernel and user time is concerned by that thread, then that means SQL Server seems fine, but it never got any CPU at all. It's a kind of an thread starvation situation where SQL Server thread never got chance to run on the CPU. We will discuss on deadlock schedulers on this video. Let's get started. Deadlock scheduler is a condition where a scheduler wakes up and in 60 seconds, if there are no meaningful work done by it, that is, it did not process anything. Let's say there are no threads placed on the runnable queue for 60 seconds, or scheduler did not process anything and all threads are suspended and are on waiter queue. It is either all schedulers getting into deadlock scheduler condition or one NUMA node getting into this condition. A deadlock scheduler scenario is reported when all SOS scheduler are reported to be stuck. Technically, this means that since the last scheduler monitor check, say about 60 seconds earlier, nothing has changed and no work is being processed. Here are some of the things that is checked. Are there any tasks waiting to be processed? Check if sys.dm underscore os underscore scheduler, the column work queue count is greater than 0. Have any new worker threads been created since last check? Or has any work been processed since last check? That is, have any new task has been assigned to the workers? If any of these condition is met, not all, the scheduler monitor declares that the scheduler or schedulers are stuck, maybe deadlocked. SQL Server can report deadlock schedulers if all the SOS schedulers on a single NUMA node are stuck, even if other NUMA nodes are processing tasks just fine. When the scheduler monitor detects a deadlock scheduler's condition, it reports an error in the error log, that is the SQL Server error log, and triggers a memory dump to be generated by the SQL dumper.exe against the SQL Server process. So let's discuss what could be the causes of deadlock schedulers. Even though many conditions can cause all schedulers to be stuck at the same time, the reason has been that the majority of the worker threads were tied up waiting for a lock resource. Blocking chains with a head blocker that you're so familiar with is the most common example. This causes the number of available SQL worker threads to be exhausted. The worker threads themselves are tied up because they are waiting for a lock, and when new task, that is work, is submitted to the SQL Server, there are no available worker threads to pick up these tasks up and execute them. Let's discuss about the possible reason for deadlock scheduler condition. As discussed earlier, locks, that is blocking, can be an main reason for this deadlock scheduler, where you have a very long blocking chain that is holding up lock, and all the threads are waiting on the lock, and this can create a deadlocked scheduler condition. Next, the reason could be due to the latches. For example, IO latches, which means there is a struck IO. Maybe there is an underlying a disk condition where the performance is very bad, maybe due to latency, and this can cause deadlock schedulers. Heavy latch chain. This could be like corroborated to a lost page insert contention as an example, where several inserts trying to access the same page due to an identity column and all trying to get hold of the same page, and this can lead to a deadlock scheduler condition. The next reason could be orphaned or unreleased page, or non-page latches, maybe commonly due to a previous antivirus exception or an assertion. This is not common, but can happen sometimes. The next reason could be due to the spin locks, maybe like orphaned or unreleased spin lock due to a previous antivirus exception or an assertion, or it could be any other exception too. Parallel queries. It is our same old CX packet or CX consumer queries. Like for example, if you have huge number of child threads spawned by a different process, and that can cause exhaustion of worker threads on the system to service one or two queries. Let's discuss on latches for this particular video. Let's get started. Consider we have a row that is getting updated using an update statement. Update statement will hold an exclusive lock till the update is complete. In the meantime, a select statement on that same row is executed while the update statement is underway. This select statement will be blocked by the update statement, as the shared lock by the select statement will be incompatible with the exclusive lock taken by the update statement. With this approach, we will ensure that the transaction consistency is completely maintained. Since we have an exhaustive lock mechanism in SQL Server, we can ensure transaction consistency completely. Now the question arises, if locking can ensure that not more than one transaction can change the data at a time, and also ensures that there will be no data reads, why do we need latches? Just to keep in mind, locks helps us maintain the logical consistency of the data, but latches helps us to maintain the physical consistency of the data. Let's discuss further here. Page is an object that is of size 8 KB which resides on disk. When you need a copy of this page in the buffer pool, that is the memory, a photocopy of this page is basically put into a buffer which is also 8 KB, and that will be placed in memory. For example, inserting value 5 comma test on table 1. I take an exclusive lock and then consider this value will be put on page 1000. Now, at the same time, if we are also inserting value 6 comma test 1 on the same table, and if we don't have a latch concept, then we will basically override the previous value with the new value. With latches, the first insert, whichever is executed, will take an exclusive latch and then change the page physically and put the actual data, and also updates the metadata on that particular page. While the other insert will wait for the previous exclusive latch on page 1000 to complete, and then takes an exclusive latch and then changes the page exactly, because we are talking about only one page, basically changes the page 1000 appropriately after the previous insert is done. Locks are for maintaining the logical consistency, that is, to maintain your database ACID properties. ACID property refers to atomicity, consistency, isolation, and durability. Let's discuss a bit on ACID properties, and then we will continue on with the latches. Atomicity. It is either all or none. That is, a transaction that is started will have to either complete to its fullest or none. This is done using an implicit or explicit transaction by SQL Server. Implicit transaction basically means like you run a simple insert or an update or a delete statement. It'll be simple or complex. What happens is like SQL Server implicitly adds an begin and commit or rollback as appropriate. As far as explicit transaction is concerned, we ourselves, the users, basically put in and begin tran and then try to complete all the transactions. And in case everything is fine, we go for a commit tran. And all these things are mentioned manually by the user. We maintain all details on the transaction log using write ahead logging, and we will be able to roll forward or roll back anytime required. Next, let's move on to consistency. Before and after any transaction, a database must be in consistent state. We enforce this by using constraints, and these constraints cannot be violated. For example, you will have to insert only integer value on an integer column. You cannot have duplicates on a primary key column, and all these things are basically enforced using the constraints that on the database. As far as isolation is concerned, all transactions performed will be isolated from one another. That is, non-committed data of one transaction should not be seen by another transaction on a read committed and a higher isolation model. This is enforced using locking and concurrency strategy. Talking about durability. Durability refers to maintaining changes on the databases even during catastrophe. This is taken care by flushing the dirty pages every now and then depending on the recovery interval using checkpoint and by performing undo and redo using transaction log. Let's look at a scenario. So let's consider we have three transactions, T1, T2, and T3. At this point in time, we have checkpoint 1. At this point in time, we have checkpoint 2. And at this point in time, we have checkpoint 3. So if you look at it here, transaction 1 basically completes here. And then we have a checkpoint 2 happening at this point in time. And transaction 2 basically has kind of completed and committed at this point in time, but the last checkpoint is like checkpoint 3 and it has happened here. And now as far as transaction 3 is concerned, it is basically running, and what we can see is like even after checkpoint 3 this transaction has not completed. So that's the reason we have mentioned it here as uncommitted. So let's consider at this point in time SQL Server restart. So what happens is like when the SQL Server comes online, the SQL Server basically checks like what was the last checkpoint, and after this checkpoint it will check like what are the transaction. And as far as T2 is concerned, since it is committed, what it basically does is like it looks at the transaction log and then it basically rolls forward all the pages or all the this particular transaction from this point, that is checkpoint 3. Now as far as T3 is concerned, that is your transaction 3, it has not completed, so it is basically like kind of an uncommitted. We have mentioned that is like it has never completed here, so SQL Server restarted. So what it basically does is like it goes to the last checkpoint, which is checkpoint 3, and after this it basically what it does is like it basically like undo all the things that has happened from here to here. So that's what happens as far as the recovery is concerned. Okay, moving on. Let's talk about latches again. What is a latch? Latches are basically a lightweight synchronization primitive, guarantees that consistency of in-memory structures. Latches are internal mechanism by SQL Server, and the user is not going to control it. It is basically controlled by the SQL Server itself. SQL Server determines which latches to use and at what time or at when. What do we take latch on? So IO latches. It basically protects pages that are not yet loaded into the buffer pool. For example, page latch IO sh shared or page latch IO underscore exclusive, which is EX. So we can see page latch IO underscore sh and page latch IO underscore EX as an example. Buffer latches, which are used to protect pages in the buffer pool. For example, page latch underscore sh or page latch underscore ex. We have other things, but we are just discussing about the common things that we can see. Next one would be non-buffer latches. These are the latches that are used to protect pages other than the buffer pool. For example, latch underscore sh or latch underscore ex. So let's discuss about the different types of latches that we have. Um there are close to like five latches, and the first one would be the destroy latch, which is DT. The most restrictive latch mode acquired when a latch is destroyed and a buffer is to be removed from the cache. Exclusive latch acquires exclusive control of a page being written, prevents all other latches to be acquired on the page where EX latch exists. Next one is update latch. It is restrictive, similar to an exclusive latch, with an exception that it allows read operation to access the page, but restricts explicitly any write operation. Shared latch. Acquired on a page when a read request issued to a page is granted. The next one would be keep latch. Keep latch, it serves to preserve a latch order record, but also to ensure that it stays in the buffer when a new latch is being placed on it. let's discuss about the difference between the locks and latches. Yeah, as far as locks are concerned, the purpose of having a lock is to guarantee consistency of the transaction, and as far as the latches are concerned, the purpose would be to guarantee consistency of in-memory structure. So that's the reason we tell like locks are used for locks are used to maintain the logical consistency, and latches are used for maintaining the physical consistency. And as far as locks are concerned, there is way users will be able to control it. For example, you can do that using different isolation levels, or you can also utilize specific query ins to control which kind of lock is required. But as far as latches is concerned, it is completely controlled by SQL Server, and users have no control over it. As far as performance is concerned, logs are kind of heavyweight because it basically holds this particular log for the duration of the transaction. You start a transaction, you take a log, and then you release that log when you basically complete the transaction. But as far as latches are concerned, it is lightweight and it is held only for the duration of the physical operation. So let's consider you're moving a page onto the buffer, and that is when what you do is like you basically do it per page basis. Like for example, if you need to change that, you basically put in an exclusive latch, modify it, and then you release it. But as far as locks are concerned, it is going to stay there till the transaction is going to complete. So that's the difference between lock and latches. Okay, let's say you have a transaction where you're updating 100 pages that has close to 1,000 rows. So what we are basically doing is that we're going to update close to 1,000 rows. And if we look at it internally, these 1,000 rows are basically stored in 100 pages. Okay, so when this transaction is happening, you will take logs on all the 100 pages till the transaction is complete. Yeah. On the other hand, you will not latch all the 100 pages at the same time. You will basically be latching only a page at a time when you are modifying it and then immediately release it. For example, if you're going to read it, you basically latch it using a shared latch, and then you will be releasing the latch on that page once that particular thing is completed. So it is basically it will be held only during the physical operation and not for the whole transaction time as far as latch is concerned. Okay, let's talk about how a worker thread is going to use latch here. Okay, so let's consider worker thread A scans table 1. It requires page 500. So that means like as far as this is concerned, it is going to just read only one page 500, which is page 500. Just for the example, I'm just using one page. It is never going to be one page as far as any transaction is concerned. But just for understanding purpose, I'm going to use only one page. So as a recap, worker thread A scans table 1, and it requires page 500. So let's consider the page is not in the cache. So what will happen is that it will basically take an exclusive latch on that page and then move it to the buffer. An exclusive latch is taken on the page at a time because while the pages are moved to the buffer, no other transaction should basically modify that buffer. Yep. For example, if page 500 is moved to the buffer, no other worker thread should move any other page to this buffer. So that's the reason we take an exclusive latch there. Yep. Once the exclusive latch is taken, we place an asynchronous IO request. After this, page IO latch underscore sh wait happens till the page is moved to the buffer. Till the page IO latch sh is there, this worker will be on the waiter queue. And once the IO completion routine is done and is signaled by another thread, let's consider here, let it be thread Y, as part of the janitor task. And this is when the page is loaded to the buffer. At this time, we release the exclusive latch and then take a shared latch as it has to read now. Yep. I'm pretty sure it will be a little confusing. I'm pretty sure on that. So what I suggest is like you can pause this and hear at least this part couple of times to understand it. We will discuss about PFS, GAM, SGAM pages, and allocation contention on this video. Let's get started. What is a PFS page? PFS page refers to page free space. PFS page maintains information on how much free space on each page is available. A PFS page occurs once in 8088 pages. SQL Server will attempt to place a PFS page on the first page of every PFS interval. The only time a PFS page is not the first page in its interval is in the first interval for a data file. File header page is the first, and the PFS page follows next. Page ID starts from 0, so the first PFS page is at page ID 1. If page number divided by 8088 is a round value, then the page is a PFS page. For example, let's consider we have an page ID in hand, and if we want to understand if it is a PFS page, so what we do is like we divide that page number by 8088, and if it is a round value without any decimal values, then it is considered as a PFS page. While we create an object, SQL Server uses the information in the PFS page to decide which page to be used for this particular object. Global allocation map page, GAM pages. In the GAM pages, which extents are allocated and which are not allocated information is basically maintained. GAM page will be the second page in the data file. Next GAM page is placed at 511230 page, that is 5,11,230th page after first GAM page or the GAM interval. If the page number minus 1 divided by 5,11,230 is a round value, then the page is a GAM page. Shared Global Allocation Map page, SGAM page. Let's discuss on this. In the SGAM pages, which extent are used as mixed extent information is maintained. When a new object is created, the allocation happens from the mixed extent, as it is understood that not all object will use 64 KB, that is 8 pages multiplied by 8 KB. In that case, instead of wasting some space for smaller objects within allocated 64 KB, mixed extents are used instead. SGAM page will be the third page. Next SGAM page is placed at 511,230 or 5,11,230th page after first SGAM page. If page number minus 2 divided by 5,11,230 is a round value, then the page is considered as SGAM page. On a SQL database server, you may notice severe blocking when the server is experiencing a heavy load. Dynamic management views, sys.dm underscore exec underscore request or sys.dm underscore overs underscore waiting task indicates that these requests or tasks are waiting for TempDB resource. Additionally, the wait type is page latch underscore whatever. Please don't confuse this with page IO latch. It is page latch underscore sh, ex or up, whatever it is. And the wait resource points to the pages in the TempDB. These pages might be of the format database ID colon file ID colon page number. So if you are seeing 2 colon 1 colon 1, then that means like database ID 2 refers to your TempDB, and the next one refers to your file ID, and the next one basically refers to your PFS page. So 2 colon 1 colon 2 is your GAM page, and 2 colon 1 colon 3 would be your SGAM page. When the TempDB database is heavily used, SQL Server may experience contention when it tries to allocate pages. Depending on the degree of contention, this may cause queries and requests that involve TempDB to be briefly unresponsive. During object creation, 2 pages must be allocated from a mixed extent and assigned to the new object. One page is for the index allocation map, that is IAM, and the second is for the first page for the object. SQL Server tracks mixed extents by using the shared global allocation map, that is your SGAM page. Each SGAM page tracks about 4 GB of data. To allocate a page from the mixed extents, SQL Server must scan the page free space page to determine which mixed page is free to be allocated. The PFS page keeps track of free space available on every page, and each PFS page tracks about 8,000 pages. Appropriate synchronization is maintained to make changes to the PFS and SGAM pages, and that can stall all other modifiers for short periods. When SQL Server searches for a mixed page to allocate, it always starts the scan on the same file and SGAM page. This causes intense contention on the SGAM page when several mixed page allocations are underway. This can really cause problems. So let's discuss what we can do to reduce the allocation contention. So as far as SQL Server 2014 and below, we can follow these below recommendations that I'm going to discuss. Increase the number of data files in TempDB to maximize disk bandwidth and reduce contention in the allocation structure. As a rule, if the number of logical processors is less than or equal to 8, use the same number of data files as logical processors. If the number of logical processors is greater than 8, use 8 data files. If contention continues, increase the number of data files by multiples of 4 up to the number of logical processors until the contention is reduced to acceptable levels. Alternatively, make changes to the workload or code. For example, convert some of your workloads that are using temporary tables to table variables, but be aware of estimate issues as far as the table variables are concerned. Maybe we can try using in-memory OLTP temporary tables instead of normal temporary tables on versions where Hackathon or in-memory OLTP is available. This specific recommendation can definitely reduce PFS contention. Again, it can reduce PFS contention. I would do this only if there is PFS contention. That's me though. Adding more files on TempDB can have major performance impact on queries where sorts are spilling to TempDB. So that's something that we need to take into account before adding many data files to TempDB. Now let's discuss how increasing the number of TempDB data files is going to reduce the contention. If you have one data file for the TempDB, you only have one GAM page and one SGAM page for each 4 GB of space. Increasing the number of data files that have the same sizes for TempDB effectively creates one or more GAM and SGAM pages for each data file. The allocation algorithm for GAM allocates one extent at a time, that is 8 contiguous pages, from the number of files in a round-robin fashion while honoring the proportional fill algorithm. Therefore, if you have 10 equally sized files, the first allocation is from file 1, the second from the file 2, and the third would be from the file 3, and so on. The resource contention of the PFS page is reduced because 8 pages at a time are marked as full because GAM is allocating the pages. Another thing that we can do is like make sure all the data files that is created on the TempDB is sized equally. That is something very critical. You cannot have different size for different TempDB files. It all should be sized equally. In case of SGAM contention, add trace flag 1118, that is 1118. Under this trace flag, SQL Server allocates full extents to each database object, thereby eliminating the contention on the SGAM pages. If trace flag 1118 is turned on, almost all new allocations are made from a GAM page that allocates 8 pages at a time to an object, as opposed to a single page from an extent for the first 8 pages of an object without the trace flag. There are disadvantages for this, so let's discuss on that. The disadvantage of using trace flag 1118 is that you may see increase in database size if the following conditions are true. new objects are created in a in a user database. Each of the new objects occupies less than 64 KB of storage. If these conditions are true, you may allocate 64 KB, that is 8 pages into 8 KB, which is 64 KB, for an object that only requires 8 KB of space if it is very, very small, thus wasting close to 56 KB of storage. However, if the new object uses more than 64 KB in its lifetime, there is no disadvantage to this particular trace flag. Therefore, in a worst case scenario, SQL Server may allocate 7 additional pages during the first allocation only for the new object that never grow beyond 1 page. So 1118 trace flag is going to be a problem for smaller objects that will be created on the database. General recommendation will be to have TempDB data and log file on its own drive, isolated from other user databases and also from other system databases. And also utilizing faster disks are really, really recommended. Now, let's discuss on SQL Server 2016 and above. Let's say like if we have contention on SQL Server with version 2016 and above, we can follow these methodologies to kind of solve it. The first one would be to apply the recent service pack and CU. Yep. And adding more data files as discussed earlier for the previous version is also something that we can definitely practice in 2016. Alternatively, we can make changes to the workload or code by converting, for example, if you have a workload that basically utilizes a lot of temporary table, then these can be converted into a table variable, or you can use in-memory OLTP temporary table. But the thing is, like, we should be aware of the table variable estimate issue. That is something that needs to be taken care. General recommendation will be to have TempDB data and log file again on own drives isolated from other user databases, and also utilizing faster disks are recommended. So core thing that as far as SQL 2016 and above is concerned, it is always good if we are on the latest service pack and cumulative update, because there are so many recommendations that are added in 2016 and above, and also like we no longer need 1117 and 1118 trace flag for SQL 2016 and above. It all comes automatically. So in case there are any allocation contention even after that, then what I understand is like applying the recent service pack and CU, and then working out on your workload can really, really help you. We will check PFS, GAM, SGAM pages using dbcc page command on this particular video. Let's get started. Let's first discuss about PFS, GAM, and SGAM page as a recap before moving on to the actual demo. So what is a PFS page? Page free space page. PFS page maintains information on how much free space on each page is available. The PFS page occurs once in 8088 pages. SQL Server will attempt to place a PFS page on the first page of every PFS interval. The only time a PFS page is not the first page in its interval is in the first interval for a data file. GAM page, Global Allocation Map page. In the GAM pages, which extents are allocated and which are not allocated information is basically maintained. GAM page will be the second page in the data file. Next GAM page is placed at 511230, that is 5,11,230th page after first GAM page or the GAM interval. SGAM page, Shared Global Allocation Map page. In the SGAMS page, which extents are used as mixed extent information is maintained. SGAM page will be the third page. Next SGAM page is placed at 511230, that is 5,11,230th page after the first SGAM page. Moving on, let's look at the SSMS and then try executing the dbcc page command. So dbcc trace on 3604 would be the first command to execute. Trace flag 3604 is basically going to print the required output in the query window. And this is going to be a session level trace flag, at least for this demo. Before proceeding with the dbcc page command, let me put in a disclaimer. dbcc page is an undocumented command. Never run this on a customer environment. I'm doing this for learning purpose, and importantly, this is a lab machine. So this lab machine will kind of be destroyed after the demo. So as far as the dbcc page command is concerned, it has got four parameters. The first parameter is your database name. Second one is your file number. Third one is your page number, and then the fourth one is related to the print output. So we are going to use number 3 here as far as the print output is concerned, as it is going to give us more details as far as the pages are concerned. So moving on, let me first execute this particular command on a database called jb underscore common underscore query underscore tuning underscore db. And the file number for this db used here is 1, and then the page number 1 will be used, which is our PFS page, and then the print output will be 3 here that will be utilized. So executing this query. The first thing that I'll be looking at is the m underscore type. Basically, for any PFS page, this m underscore type will be 11. So moving on, what we can see is like the output basically shows us like uh, it starts with a page number of 0, and as we know, like each PFS page holds the information of 8088 pages. It starts with page number 0, and let's look at like what it is ending at. As expected, what we are able to see is like it is 8087. Since the page numbers are starting from 0, 8087 plus 1 would be 8088. So it is pretty sure like each and every PFS page are tracking close to 8088 pages. So if we look at the pages, like as far as this particular information is concerned, what we are able to see is like pages 1 to 0 and till page 1 to 3. That is like pages 0, 1, 2, and 3 is mentioned as allocated here. So we know like a 0, page number 0 is your page header, 1 is your PFS page, page number 2 is your GAM page, and then page number 3 would be your SGAM page. So if we look at it here, we will be able to understand like which pages are allocated and which pages are all not allocated. And for the allocated pages, we can further see how much percent it is full. And also, it basically gives you the information whether these pages are part of an uniform extent or mixed extent. So that's on the PFS page. Let's check the GAM page for this particular database. So the first thing again, I'll be looking at the m underscore type, which is 8 here. So that implies m underscore type will be 8 for all the GAM pages. Yep. And then here, what I'm able to see is like we are able to see the extents here for the GAM page. And let's just pick up this 1 0 and then 1:584. So what this means is like the 1:0, which is this one, it basically tells that this is the first page of the first extent in this range. And as far as 584 is concerned, this is the first page of the last extent in this range. And now if you see here, we have a value of 584, but the next line basically shows as 592. So that means like from 585 to 592, 591 pages are there. Like that is basically like refers to the last page of this extent. That is like 591, 1:591 would be the last page of this extent. So moving on, we will be able to understand which pages are allocated and which pages are not allocated. So that's the information that we will be able to see here. So all the extents within the range that, for example, let's pick up maybe this one. I think like let's pick up this one. Okay, so all the extents within the range, including the first extent and the last extent, are allocated as an are all allocated kind of. So this is the information that we are seeing here as far as the GAM page is concerned. It contains all the information about the extents and pages. So it tells us like which pages are allocated and which are not allocated. So that's the information that will be required. And moving on, let's look at the SGAM page. I'm going to run that same command, but the only difference is like I'm changing the page number to 3. So now if I look at the SGAM page, m underscore type would be 9. So that means like any page which is considered as a SGAM page will have a m underscore type of 9. So now if I look at the SGAM page information here, so again, this particular information that we are seeing, 1:0 refers to the first page of the first extent in this range, and as far as 1:182,608 basically refers to the first page of the last extent in this particular range. And what I'm seeing is like there is a as far as the value 1:182,615. So to repeat it, 1:182,615. That is the previous page to this is the last page of this particular extent. So that's the information that is provided here, and this basically tells us if we take this particular range, what it basically tells is like 1:182,616 is the first page of the first extent in this range, and 1:182,624 is the first page of the last extent in this range, and again 1:182,631 is the last page of this extent. So as far as this particular line is concerned, what we can imply is that all the extents within the range, including the first extent and last extent, are allocated as mixed extent or uniform extent. That's on the SGAM page. Let's try creating a new database, and then let's look at the DBCC page command. So I'm going to create a database called JB page. Now what I'm going to do is like I'm going to alter this JB page database, and will enable mixed page allocation on. Yep. And then what I'll do is like I will create a simple table which basically has two columns. One is integer and second one is a varchar 8000. And then I will be inserting only one row into that particular table. So what I'll do is like I would do a cross apply between this table, that is the one that we created, with the function physlog_cracker, and then I will basically be checking if what is the page allocation type, and also like I'll be checking what is the page number as far as this particular row is concerned. So if I run it, I'm able to see the data. File ID is 1, we know that, and page ID is 327, and is mixed page allocation is set to 1. So that means like the data, that is the pages that has come for this object, is from the mixed extent. So the page number we know is 327. Let me turn on a trace flag 3604. And then what I'm going to do is like I'm going to key in the database name, file ID 1, page ID 1, which is your PFS page, and then the output print output option would be 3 for verbose. Like maybe you get good amount of information other than the other parameter. Okay, when I run this PFS page, as expected, m underscore type is 11, so we know like it's a PFS page. Now, we know that we are worried about 327, and that is where this particular row is inserted. So what I'll do is like I will directly go to that particular page and then see what is what can be seen there. So 327. So if we see here, what I'm able to see is like, since the page starts from 0, I'm not looking at 327, I'm looking at 326. So what I'm able to see is like the PFS page basically shows that page number 327 is allocated and it is 80% full. So basically SQL Server utilizes this particular PFS page and will understand which pages are available and which pages are full, and depending upon that, understanding like whether these pages are coming from mixed extent or from the uniform extent, what it does is like it allocates those pages to the incoming object. So that's how it works. So moving on, let's look at the same one. Instead of a PFS page, I'm going to check a GAM page, which is your global allocation map page. So if I look at it here, so what I can see is like um, this particular extent, as we discussed before, 1:0 basically points that that's the first page of the first extent in this range, and then 1:336 is basically telling like it's the first page of the last extent in this range, and then 1:343 is the last page of this extent. That is not seen here, so it is implied. So now that it is like 336 and here we have 344, so the last page before this is 1:343, which is the last page of this extent. So what we can see is like we are able to see like this particular page, which is 327, which will be seen as 326 here, which is among this range, is shown as allocated. Yep. And moving on, let's look at the SGAM page. What I'm able to see, M underscore type is 9 as expected. And then here, what I'm able to see is like we know that this particular range it's showing as not allocated, but if we look at this one, this is where it becomes interesting. So what I'm able to see is like 1:320, which is your first page of the last, which is the first page of your first extent in this range, and then it basically ends at 327. That is the page that we are interested, and it is basically like since the page starts with 0, we are interested in 326, but this particular range basically shows as allocated, as we know, because we have created the table and then the row is present in 327 page. Since the page starts with 0, so we can imply it as 326. So this is what we see as far as the SGAM is concerned. If I look at it one more time as far as the PFS page is concerned, we know like each PFS page keeps track of 8,088 pages. So what if I put in a value of 8088, which we know is going to be a PFS page? Let's try running that one more time. And if I run that, as expected, the M underscore type is equal to 11. And then now if I look at it here, what I'm basically able to see is like it starts at 8088, and what I'm able to see is like it is 16,175. So we know like the page number starts with 0, so that means like 16,175 will be implied as 16,176. So I'm just going to add 1 here because page number starts with 0, and then divided by 8088. And here you go. It is in a whole number. You don't see any decimal point. So that shows you that the PFS page tracks 8088 pages. We will discuss about memory on this video. Let's start with 32 and 64-bit operating system. 32 or 64-bit that we are referring to are the bits that can be used for addressing the address space. For example, a 32-bit CPU can address only 2^32 byte of memory, which is 4 GB. Servers that are running a 32-bit operating system have 4 GB of total virtual address space, which is called VAS, which is divided evenly by default into 2 GB of kernel mode VAS and 2 GB of user mode VAS. Applications can only allocate memory from user mode VAS, which significantly limits their ability to access memory in a 32-bit process. If an application is compiled with large address-aware flag, like SQL Server is, it can address memory beyond 2 GB through the use of two different options available in Windows Server. The first option is /3 GB or 3 GB tuning option that exists to change the VAS split from being 50-50 to being 2575 for kernel mode and user mode VAS. Basically, you take 1 GB away from the kernel and give it to the user mode processors, allowing them to make use of more memory, but only up to 3 GB. The other option is address windowing extension or AWE, which leverage page address extension to make use of 36-bit pointer instead of a 32-bit pointer, allowing you to access memory beyond 4 GB up to a maximum of 64 GB. This requires using memory through page table entries in the kernel to map the address spaces above 4 GB. If you make use of /3GB tuning, this restricts the available PTE such that the maximum amount of addressable memory is limited to 16 GB. A 64-bit process has 16 hexabytes of calculated user mode address space. But since this is beyond any reasonable amount of memory, it is limited by 64-bit operating systems to 24 terabyte for latest operating systems, which is still well beyond the limits of any physical server's configured RAM. This allows SQL Server to allocate all of the memory on a 64-bit server without any special configuration, since calls to virtual alloc have to be backed by user mode VAS. A byproduct of this is that all of the memory allocated by calls to virtual alloc is pageable by Windows. So if it thinks it is in memory pressure, that is the operating system, it can page out the entire SQL Server process, resulting in significant impact to performance. Because of this, 64-bit servers can leverage the AWE API calls that are previously needed under a 32-bit process to prevent paging of the process by using lock pages in memory to lock the pages from the OS being able to page them. This is very specifically locking pages and not AWE. The underlying Win32 API call happens to be the same. Allocate user physical pages, but it does not require enabling AWE on a 64-bit server. It just requires the lock pages in memory user right assignment in the local security policy. 32-bit is kind of obsolete now, so my videos on memory will focus only on 64-bit. Let's discuss on physical and virtual memory. Consider I have a 4 GB server. That is a server that has got 4 GB of memory. Out of this, let's consider 2 GB is utilized by operating system and the device drivers, and rest 2 GB is for the application use. A developer cannot make direct physical memory allocation by writing an instruction to make memory allocation directly on the physical memory. There is high possibility some other application can override that, causing issues if physical memory allocations were allowed to applications directly. For example, we cannot make physical memory allocation like, let's consider 2 to 2.5 GB is for VLC player, 2.5 GB to 3 GB is for Edge browser, 3 to 4 GB is for SQL Server, as we may not know how many applications will be installed on the server, and not all applications can have direct physical memory allocation reserved. Also, getting a continuous chunk of physical memory is not practically possible. What Windows or any other operating system does is it provides empty address space for all the applications. Since our example is on a server with 4 GB physical memory, Windows will basically advise applications that each application has a 4 GB of virtual address space. Now, whatever memory allocation the application has to do, it will utilize the VAS, and OS will take care of the address translation for these virtual address to physical address that is on the physical memory. That is the physical address that I'm referring here is basically the physical memory. For example, let's say application 1 allocates address 100 and application 2 again allocates address 100. So just to understand, each and every application will be getting its own VAS. Yeah. Remember, these are all virtual address space, and also each application will get 4 GB VAS as the available memory is close to 4 GB. But the operating system will translate the physical memory for application to example address XYZ, and for application 2 to address ABC. Consider this is my virtual address space and this is my physical memory. So the Windows operating system uses a page translation table to perform the virtual to physical address translation. Let's consider when we allocate a 4 KB page on the VAS, and let's assume, for example, this is at the address X008. Windows will capture this info on the page translation table that VAS address X008 from process R has physical memory allocation at address X023. And this is captured in the page translation table, as you can see here. Moving on. Going back to our example of 4 GB VAS, where 2 GB is taken by the operating system and 2 GB is utilized by your user process. We know that the server has 4 GB physical memory, and we also have a page file which is considered to be an extension of our physical memory. This page file will be placed on your disk subsystem. Let's consider Chrome uses close to 700 MB memory, and then Outlook uses another 800 MB memory. Now let's consider VLC player is requesting 1 GB of memory as it needs to play a huge movie. In this case, Windows using LRU method, that is the least recently used method, will move some of the pages of Chrome and Outlook to the page file, and then it allows the VLC player to utilize the requested 1 GB memory. Now let's say we stop the video and then open Chrome to browse something. In that case, Windows will basically move the required pages for Chrome, and if those pages are on page file, it basically brings it back from the page file to the memory. This is the reason we call page file as an extension of physical memory. So now, how much VAS do you have on the database server or on any particular server? It will be an amount of memory plus the page file. The amount of VAS you can have is the amount of memory plus the amount of page file. We will continue discussing about memory on this video too. Every process that allocates virtual address space has private bytes and shared bytes. So as an example here, what I'm able to see is, like, as far as application R is concerned, we are able to see private bytes as well as shared bytes here. Okay, let's discuss what is a shared byte. There are some parts of the code that can be shared by multiple processes. For example, let's take a look at this particular notepad file. When I click on file and then click on open here, I'm able to see this particular open dialog box. Same way, when I open this MS Paint and then click file and open, what I'm able to see is, like, I'm getting a corresponding open dialog box. Now, when I compare this open dialog box with the one that is open for Notepad, what I'm able to see is, like, both these are kind of very, very similar, except the icon that I'm able to see here. So this is for Notepad and this is for MS Paint. Other than that, everything seems to be same. So what I understand is, like, so any code that is basically going to be like used by several applications to achieve its functionality, in our case here, this open dialog box, all these things are kind of shared code, and these shared code will be placed on the shared bytes. With slight modification, that is, using a variable name in the common code that changes with each application to use the same code for several applications such as MS Paint, Notepad, PowerPoint, Word, and much more. So this code will be on the shared bytes of the memory, which can be reused by appropriate application. That is, the memory area which can be shared with other application or process and is called shared bytes. Let's discuss about private bytes. Private bytes, as the name implies, are process memory which are solely used by that particular process and at any point of time cannot be shared with other application or process. Let's now discuss about working set. Working set is a memory allocation for that particular process and that can be paged out. If you open Task Manager, memory that we can see is the working set value for that particular process. So if we look at any process here, what I'm able to see is like the memory that we are seeing here is basically the working set value. SQL Server has got two memory allocation model, and they are conventional memory model and log pages in memory model. We have large pages memory model also, which we will be discussing later. Let's consider we have 250 GB memory on a database server. Consider we have conventional memory model for the SQL Server, which is the default memory model, and max server memory is set to 200 GB. Now, let's consider SQL Server is using all memory available to it. If you open the Task Manager and check for SQL Server memory utilization, it will show it the memory utilization for SQL Server process to close to 200 GB. On the other hand, if we have locked pages in memory model for SQL Server and max server memory is set to 200 GB. Now let's assume SQL Server is using all memory available to it. If you open the Task Manager and check for SQL Server memory utilization, it will show it as close to 1 or 2 GB. That is the memory utilization by SQL Server on the Task Manager. It will basically be showing as 1 or 2 GB. Now, if someone updates you that SQL Server is allocated more memory, but it never uses more than 1 or 2 GB, I'm sure you know the answer for it now. As SQL Server uses log pages in memory model, the value we are seeing on the Task Manager is just the working set value of the SQL Server and it can be paged out. But the allocation made by SQL Server using log pages in memory model cannot be paged out. What is this 1 or 2 GB that is used by SQL Server that is visible on the Task Manager when SQL Server uses log pages in memory model? This memory is used by your worker threads on a 64-bit machine. Each worker thread uses 2 MB memory. Link server queries, for example, you have a huge link server query. The memory used by that will be reflected here on the Task Manager. Log pages memory allocation will be purely for your buffer pool allocation. So to keep in mind, page allocation memory comes from log pages in memory area and non-page allocation memory gets its share from the memory as shown in the Task Manager. Let's discuss what is conventional, log pages, and large pages memory model. Anytime SQL Server will start, it will reserve and commit the memory. Whenever SQL Server starts, it reserves the max server memory on the database server, but commits required memory only as and when required. For example, let's consider I'm planning a trip. So for this trip, I will basically book an air ticket. So this is an example for reserving. I will commit to it only if I travel on that day using that ticket. In this case, I have a plan for travel, so I will intimate the airlines and book a ticket well before, and that actually gets into action only if I travel. So let's discuss about the three memory models. So as far as conventional memory model, log pages in memory model, and large pages memory model is concerned, conventional memory model, we use virtual alloc for allocating memory. We will discuss about virtual alloc and other APIs in some time. But as of now, conventional memory model basically uses virtual alloc for allocating memory. As far as log pages in memory is concerned, we use allocate user physical page for allocating memory. And as far as large pages memory model is concerned, we use allocate user physical page API for allocating memory. Difference is it reserves and commits all memory as set in max server memory as soon as the SQL server starts. Page size will be 2 MB and these pages cannot be paged out as we have log pages in memory set. As far as large pages memory model is concerned, it needs enterprise edition of SQL Server, at least 8 GB of memory. And as we know, log pages in memory should be set. And once the trace log 834 is enabled, we will be able to use large pages memory model. SQL Server will fail to start if contiguous chunk of max server memory value is not available on the database server. For example, let's consider the database server is running for several months or something. And for example, if you restart the SQL Server, there is a high possibility SQL Server will not start because it will not be able to commit all the memory that is mentioned in the max server memory. So because it might not be getting the contiguous chunk of memory, maybe because of memory fragmentation and things like that. Now, if you try restarting the server, there is a high possibility that SQL Server will be able to make the a commit for that particular memory what is mentioned in max server memory, and then it will be able to start it. And as far as conventional memory model is concerned, pages can be paged out, and lock pages in memory and large pages memory model, the pages cannot be paged out because we have this lock pages in memory option enabled for the SQL service account. Now, as far as the conventional memory model is concerned, you will be seeing a message called a significant part of SQL Server process memory has been paged out, and this may result in a performance degradation. So what it basically signifies is that whenever operating system feels like there is a memory pressure, it basically pages out all the required applications process memory just to make sure like operating system has got a good amount of memory. So as far as SQL Server is concerned, when this particular page out happens, as far as SQL Server memory is concerned, there is high possibility all your costly pages and all your costly plans will all be like removed from memory, and that can definitely cause performance issue. So in order to avoid that, we basically what we do is like we enable log pages in memory model, and also like we need to make sure like there is no other memory hungry application on the database server that is actually required for the database server. Moving on, um, let's look at what is virtual alloc and user allocate physical pages, and then we will take it from there. So as far as virtual alloc function is concerned, what we can see is like it basically reserves, commits, or changes the state of a region of pages in the virtual address space of the calling process. Memory allocated by this function is automatically initialized to 0. Now, let's look at the remarks and see if we can get more details on this particular thing. So as far as the remarks is concerned, what I'm able to see is like each page as an associated page state. Virtual alloc function can perform the following operations: commit a region of reserved pages, reserve a region of free pages, simultaneously reserve and commit a region of free pages. Virtual alloc cannot reserve a reserved page. It can commit a page that is already committed. This means you can commit a range of pages regardless of whether they have already been committed, and the function will not fail. So now let's look at the syntax for virtual alloc. So what we can see is like we are able to see like on the virtual address space using virtual alloc, we will be able to basically put in an address for this particular function, and then you need to mention the size, like how much you want as far as the VAS is concerned, and also the allocation type. For example, are you going to reserve or you're going to commit and things like that, and then protect. Basically, like you will tell like whether it is going to be read write or read only and things like that. Moving on, let's look at allocate user physical pages. So what we are seeing is like uh, allocate user physical pages allocates physical memory pages to be mapped and unmapped with any AWE region of a specified process. That is what we are seeing. And as far as the remarks are concerned, what we can see is like the allocate user physical page function is used to allocate physical memory that can be later mapped within the virtual address space of the process. The set lock memory privilege must be enabled in the caller's token, or the function will fail with this particular error. So this is what we are seeing as far as allocate user physical page is concerned. Moving on, let's look at the SQL Server error log. So this is a cleanly newly installed SQL Server. So now when I query the SQL Server error log, what I'm able to see is like let's look at the basically the memory model that I'm using right now. So what I'm seeing here is like I'm basically using a conventional memory in the memory manager. That let's try implementing the log pages in memory and then see what happens after restarting the SQL Server. So to enable log pages in memory, let me check what is the SQL Service account. So in my case, it is JBS Wiki. So what I'll do is like I will go to the user rights assignment and then open log pages in memory and then add the SQL Service account here. It is added here. So now what I'm going to do is like I'm going to restart the SQL services. Let it complete here. It's stopping the service right now. In some time, it will start the SQL Server. Just give it like another 30 seconds. Once this is restarted, what we'll basically do is like we will query the SQL Server error log, and then we will see like what is the memory model used. So right now it is restarted. So let me run this. Then let me check what is the memory model using. So right now what I'm seeing is like it is no longer conventional memory model. It is right now using log pages in memory manager. So now we know like how do we enable log pages in memory. So next one, what we'll do is like we will try checking what if we have what kind of things that we need to do as far as large pages is concerned. So right now we know like we have all the prerequisites here. So if I add a trace flag onto the SQL server, so let me stop it. Once this is stopped, what we'll do is like we will try adding a trace flag called 834, and then let's see what happens as far as the memory model is concerned. So I've stopped it. So let me try adding a trace flag called 834, and then let's apply it. So let me start the SQL Server. Once the SQL Server comes online, what we'll do again is like we will check the error log and see what is the difference right now. So if I look at it now, what I'm able to see is like I'm able to see large pages in the memory manager. So that's the difference. So initially, when the SQL services started, after I installed the SQL Server, I was able to see conventional memory model, and then I enabled the log pages in memory model by adding the SQL service account to the log pages in memory user assignment policy. And after that, what I did is like I just added a trace flag 834, and I was able to understand like once that was done and reset the SQL services, it is right now using large pages in the memory manager. So that's the difference. Okay, as far as the next question is concerned, let's understand, like, for example, when log pages in memory or large pages is enabled, let's consider we look at the task manager and we will be seeing like 1 or 2 GB memory utilization. So how do we know how much memory is utilized by log pages in memory and large pages memory model? So one thing is like to look at the performance monitor, and then let's do that now. So let's open the perfmon, and then if I add the memory manager target server memory, that will give us the information. That is one way of checking that. So I think we should go to memory manager here. Yep, here it is. And then if I go to the target server memory, so let's see what is target server memory. It is the ideal amount of memory the server is willing to consume. And what about the total server memory? This is the total amount of dynamic memory the server is currently consuming. So what we'll do is like we'll try adding this, and then we'll change this to a report. So what we can see is like it's in KB, so close to 4 GB is utilized by the SQL Server. So the other way to check this is like to run this DMV sys.dm underscore os underscore process memory. this give you good amount of information. So what it basically tells us like this is the overall physical memory used by SQL Server. And this basically shows you the large page allocation KB as far as SQL Server is concerned. And then this is locked pages allocation KB. So this is another way to check that. And another way is to run a DBCC memory status. So it gives you the information. So if you look at this, it basically tells you like how much physical memory is there, what is the virtual memory and things like that. And what you will be able to see is like you will get a good amount of information as far as memory is concerned. Now, if you look at this, what we can see is like we will be able to see like how much log pages is allocated, how much large pages are allocated. So you can either use this method, which is your DBCC memory status. The better way would be to use this particular query, and then you will be able to understand, at least to understand how much large pages or log pages is allocated for SQL Server is concerned. But to be frank, DBCC memory status has got wealth of information as far as the memory allocation is concerned by the SQL Server. It tells you like each and every clerk that is utilizing memory. We will continue discussing about memory on this video too. Let's discuss about buffer pool. Buffer pool is where memory is allocated by SQL Server primarily for caching, data and index buffers. Memory reserved for the buffer pool can be given to other memory consumers and will be called stolen memory. Buffer pool uses most of the memory in SQL Server process, and SQL Server aims to cache and keep cached any page that is accessed by maximizing overall performance by minimizing disk I/O. All buffers are 8 KB in size. Buffer pool can grow till available memory on the database server. It is reserved at the startup and will grow till available database server memory size, regardless of the configuration settings. Max server memory controls buffer pool size only and controls how much memory is committed with buffer pool. Max server memory can be changed dynamically as it is fully reserved already. Minimum server memory value will not be committed while SQL Server starts, but once the memory allocation of SQL Server moves past that value, it will never come down from the minimum server memory value. Stolen memory is the memory consumed from within the buffer pool for things other than data and index pages. Stolen memory consumers can include procedure cache, query reservation memory, that is the memory used for sort and hash operation, optimizer memory, lock memory, and much more than that. SQL Server memory utilization outside of buffer pool can be from worker threads. Each thread will be 2 MB for 64-bit and 4 MB for IA64. Extended stored procedures, link servers, COM objects or DLL used by SP_OA procedures, CLR engine, etc. Let's discuss on DBCC memory status. We will be using this command dbcc memory status, and that will provide us all the information as far as SQL Server memory utilization. So let me execute that. This is the output that we are seeing. So what we are able to see is like the available physical memory is close to like it's basically given in bytes, so it is close to like 24 GB. So let me copy this value. Then if I put it here, so I'm basically converting it to KB, MB, and GB. So if I run that, it's close to 24 GB. So the available virtual memory, it will be like too huge because it's vast, not the physical memory. And this is the amount of value that is available as far as the paging file is concerned. Again, it is mentioned in bytes. Next one is related to the working set. So this value is again in bytes. And what this value signifies is like this would be the same value that you will be seeing in your task manager for the SQL Server process. So let me put that here. And what I'm seeing is like I'm seeing close to 118 MB is currently used by SQL Server as far as the working set is concerned. So now if I look at the task manager, what I can see is like it is same as what we have seen. It is close to like 120. If I convert it, it would be around 118 to 119 MB. Moving on. So this one basically tells like percent of committed memory with respect to the working set, which basically tells us 100%. The next one is like basically we are seeing like the system physical memory high. So that means like there is no issues, and what we can see is like there is no external memory pressure here. So external memory pressure is something like that happens outside of SQL Server. For example, if some other application or the operating system driver, if it is utilizing much of memory, then there is a high possibility that can cause memory issues, wherein that would raise in memory pressure, and SQL Server, including all the application on the database server, will have to reduce its memory utilization. So as far as our values are concerned, we are seeing like system physical memory is high, and that is set to 1. So that means like there is no memory pressure. So in case if in the output, if you are seeing like one value 1 for system physical memory low, then that implies that there seems to be an external memory pressure. And as far as processes are concerned, that is specifically for SQL Server, in case if you see process physical memory low, then that means like it signifies that there is an internal memory pressure. And same way, in case if there is an value of 1 set for this one, it signifies like there is an memory pressure as far as the virtual memory is concerned. This is highly unlikely, but it can happen sometimes. Moving on, what I'm able to see is like as far as the memory manager is concerned, I'm able to see like VM reserved is this much. This basically tells like this is the virtual memory that is reserved. So as I told you, like when SQL Server starts, it basically kind of reserves the memory, and depending upon the requirement, it basically commits the memory. So here, what I'm able to see is like the memory that is virtual memory that is reserved is this much, and the memory that is committed is this much. So this is the value that we are able to see here. And next one, what we are able to see is like this is the amount of memory that is committed by log pages, and this is the amount of memory that is used by the large pages. So in our case, we have implemented large pages with a trace flag of 834. So that's the reason we are seeing it. So emergency memory, this is basically for your DAC connection. Just in case if you need to take a DAC connection, this emergency memory will be utilized by that. So as far as this target committed and current committed are concerned, these are the very important things. So what we can understand from here is like basically target committed is like this much of memory in KB, and current committed is basically like this much of memory in KB. Target committed, what it basically tells us like this value changes as per the memory pressure or the available memory. If there is no external memory pressure, then this value basically increases. This is same as your target server memory in performance monitor SQL memory manager in the performance monitor. And as far as the current committed is concerned, it is basically like it basically tells like how much memory SQL Server is using. If the target comes below total, that is the target committed comes below total, then that means we are seeing external memory pressure. Now, the total will trim its memory use and tries to match the target value. And this current committed is same as your total server memory in performance monitor SQL Server memory manager. So this is a little important. As long as target and current is same, or current is below target, everything seems to be okay. Maybe like when current committed is less than target committed, there is an understanding like it is trying to grow. But in case if target committed is less than current, that means like we can clearly understand like there seems to be an external memory pressure, and due to which The target committed has come down, and now the current committed as whole should also come down, should match target committed. So this is something that we need to really look at when we have the dbcc memory status command. So other things are like self-explanatory, pages allocated, pages reserved, pages free. So this pages free basically tells like whatever we have reserved, these are the amount of pages that are free, so that in case in something comes up, like for example a new requirement comes up, then these free pages can be utilized. For example, if you see free pages as nil, then there is a possibility like there is a problem on the database server. Moving on. So these are the informations, like we will get the same information as this. The only thing is like you will get the information for the number of NUMA nodes that you have on the database. So right now I have one NUMA node, so I'm getting the information for that. And we have a lot of clerks here. Each clerk will have its own memory utilization. When there is an issue, for example, there is a 701 out of memory error, then we can look at the things that we just discussed and then understand if it is an internal memory pressure or an external memory pressure. And then we can look at the individual clerks and understand which particular clerk is taking much memory. And depending on that, we will be able to troubleshoot it further. So moving on, we have other things like SOS Manager, Bitmap, SQL General, SQL buffer pool is here. So basically the buffer pool kinds of give us the information like how much is reserved and how much is committed, and also like how much is the log pages allocated. So this is something that can come handy to understand like if SQL buffer pool is utilizing much memory. And as far as query plan is concerned, this clerk basically utilizes a kind of a plan cache where you place your plans. Moving on, SQL Optimizer. This basically contains the information with regards to optimizing the query. So, for example, when you are creating the execution plan, you basically have to use this memory to create. The optimizer requires memory to perform optimization and create the query tree, and that information will be present here. Moving on. As far as procedure cache is concerned, we see that total procs, and this value shows the total cached objects that are currently in the procedure cache. As far as total pages is concerned, this value shows the cumulative pages that you must have to store all the cached objects in the cache. In use pages, this value shows the pages in the procedure cache that belongs to procedures that are currently executing. This talks about the query memory usage. Query memory is also known as workspace memory. If the size and cost of a query satisfy small query memory thresholds, the query is put in a small query queue. This behavior prevents smaller queries from being delayed behind larger queries that are already in the queue. So the grants here, it basically is the value, shows that the running queries that are memory grants. Waiting is value that basically shows that the queries that are waiting to obtain memory grants. Available refers to the buffers that are available to queries for use as hash workspace and as sort workspace. Maximum, this value shows the total buffers that can be given to all queries. Optimization queue basically gives us a summary of the users who are trying to optimize the queries at the same time. So queries are submitted to the server for compilation. The compilation process includes parsing, algebraization, and optimization. Queries are classified based on the amount of memory that each query will consume during the compilation process. When a query starts, there is no limit on how many queries can be compiled. As the memory consumption increases and reaches a threshold, the query must pass a gateway to continue. There is a progressively decreasing limit of simultaneously compiled queries after each gateway. The size of each gateway depends on the platform and the load. Gateway sizes are chosen to maximize scalability and throughput. If the query cannot pass a gateway, the query will wait until memory is available, or the query will return a timeout error. Additionally, the query may not acquire a gateway if the user cancels the query or if a deadlock is detected. If a query passes several gateways, the query does not release the smaller gateways until the compilation process is completed. This behavior lets only a few memory-intensive compilations occurs at the same time. Additionally, this behavior maximizes throughput for smaller queries. SQL Server will free memory under external or internal memory pressure. External memory pressure, it's outside of SQL Server. Operating system basically notifies all application, including SQL Server, of memory pressure and requests them to free up the memory. Internal memory pressure occurs when buffer pool is exhausted and more memory is needed. That's it for this video. Thanks for watching. Have a great day. Jai Hind.